All right, we'll get started. So announcements, I believe someone in here has something to remind me of. Oh. It's okay, I remembered. I'm amazed myself. I typically have somewhat unstandard office hours in that I just try to service everyone from the same class at the same time. And that way it parallelizes, you can learn from each other. You're not sitting there waiting as one person gets their question answered and then one person gets their question answered, et cetera. But I've been talking to people and it seems like it would be useful to just have a big review slash practice problems time and start to schedule that on a weekly basis. So we decided that we're going to start doing that today. And then I'll talk to people about days that would work in office hours, just kind of gather and have days that are this class's time or mostly dedicated to this class's time to solve some extra homework problems, etc. So that's the plan to start today, and anyone who wants to attend that is more than welcome. Not to be for one person, but for anyone who just feels like they could use some extra practice or get some help on homework. So I will have that after my next class. So an hour after this class ends, I will be in my office for an hour to go over practice problems and do the best that I can to make sure that you're prepared for the upcoming exam that's a week from Friday, as well as the homework that we do between now and then. So feel free to join me. We have a homework due on Wednesday. Thank you to those who reached out while Canvas was down to ask for the document. I didn't have the exact document that our TA has made in LaTeX, taking my hack together screenshots from the book and turn that into an actual document. So I had to send the hacked together PDF to those who reached out to me, but thank you for those who did. If Canvas being out for a day creates a problem for you, which it happens, I'm happy to give you a day's extra time, but reach out to me on an individual basis because the next assignment that we're going to get is going to take us right up to and be right up against the next exam. So I want to offer people the chance to turn that in early. I want to offer people a chance to get that in and get feedback on it before the next exam. And if you take an extra day for this, which I do want to allow you to do, it gives you one fewer day to work on the next assignment for that's due before we think about that for the next exam. So just try to keep on top of the work that has to keep coming because we're on the quarter system and there's no time for a breather in between anything, which is unfortunate, but I will work with you to make that work for your schedule the best that I can. Any other questions before diving back into NPDAs? All right, away we go. Last time we solved this NPDA right at the end of class. That was for the WWR language. So we needed rules to divide this up into what might seem like the algorithmic steps to solve the problem. So we had pushing W onto the stack, guessing where the middle of the string was. Non-determinism helped us with that. And then we need to match the reverse of the string against whatever is on the stack when we guess that middle. And as long as there was a single path to acceptance, then we accept the string. I kind of drew out a thread diagram, a thread tree is how I like to think of these kinds of problems, where at each potential middle point, we fork the process, which branches tree, and each one carries forward a new thread, which can become multiple threads as we continue to parse the string. We have kind of a flow diagram of all of the running threads. And that way we can determine, is there an accepting thread? As soon as we find a single accepting thread, then we have acceptance. Were there questions on any of those ideas or something that I can revisit or go over in more detail? You seem dead, but it's like Monday in here.
Just Monday part two.
right? That's how I feel about Tuesday. It's my least favorite day of the week. Yes. I've been a fan since the 90s. Fan in air quotes. I've been emotionally abused by the Mariners since the 90s.
Brian was pissed.
Yeah. The Julio scream in the background during his peak. You weren't thrown a strike and you struck out. I would be screaming too. Anyway, that's outside of the scope. Yes. We can think about this as a sequence of transitions, not just drawing it as a transition graph. So instead of drawing it as a transition graph, I decided to here at least show here are the sequences of transitions, and kind of like assembly instructions or methods, you can divide a state machine down into the associated rules that match to some algorithmic idea. So you can think of this as kind of like program decomposition, where we have rules for each algorithmic idea, pushing W onto the stack, guessing the middle, matching the reverse against the stack, and recognizing a successful match. So those are the associated transitions in transition list form that would get you to that point. I'm trying to drain these markers at the same time, so I'm taking guesses as to which ones still have good juice in them. Things that go through your mind in the middle of a lecture. It's a Tuesday for me too. So the next thing we're going to learn how to do is translate a context-free grammar into a non-deterministic pushdown automaton. As you might guess, because these recognize the same class of languages, as soon as you have some kind of context-free language, you can both make a context-free grammar and draw or write the transition rules for an NPDA that will accept that. So there must be an equivalence between an associated context-free grammar and some non-deterministic pushdown automata. If they represent the same idea, the same power, then we should be able to convert one into the other. The question is just how easy is it to do that? And it turns out that one of the grammar rules that we have studied, grammar forms that we've studied, actually map perfectly onto how we would want to represent it as a non-deterministic pushdown automata. And it's the other one than the one we talked about before. So yes, this process is actually quite straightforward if the grammar is in Grimach normal form. So we're going to assume that we have a grammar in GNF, and we're going to show how to convert a grammar that is in GNF into an NPDA. And I can also state that any grammar that we are given in that is a standard context-free grammar can be converted into GNF. Once it's in GNF, we proceed with a leftmost derivation of each production. As we do a leftmost derivation, that will define and specify the transitions of the NPDA, which is really cool. So let's see how that actually works. So let's start with a question, constructing a pushdown automata, accepting the language given by this. So let's first convert the grammar into GNF. Anyone want to try to take a stab at this, just intuitively? Go ahead and take a couple minutes. If we remember what GNF is, anyone remember the GNF rules? Non-terminal arrow, single terminal followed by one or more zero or more non-terminals. So you have at least one terminal, it is exactly one terminal. And following that exact one terminal, we have some number of non-terminals. So see if you can intuitively convert this into GNF. Do the rules make sense? Single terminal, zero or more non-terminals for every production.
I didn't take the B and break it up into another non-terminal,
Yeah,
because I can only produce one B, I have to make another non-terminal.
yeah, so this portion of S is in GNF. This portion is in GNF, so we really just need to worry about this BB right here. So if we kind of recursively take a look at this, we're gonna pull over the S, we get S arrow, A capital S, and now we need to do something to this. For the moment, we're just gonna give it another non-terminal that's gonna represent that. And so this production is now in GNF. But we now need to define this capital A. Now we can't just make this BB because we can't have more than one terminal. So we can make a single one of them, but then we need another non-terminal to represent that. And that can be the remaining B that is there. So that is this grammar in GNF. Does that process make sense, or does that logic make sense? I didn't give you the rules for exactly how to do that, but it's a recursive process where you just look for and break apart anything that is after a portion of this in GNF, and then start to break that down into the first terminal that you can make, followed by another non-terminal representing the rest, as long as that's a sequence of terminals or contains a sequence of terminals. But this will get you to GNF, which I think I have on the slide. Yeah. I think it's exactly what I wrote. So what's nice about this is we know the very first thing that we do is start with the start non-terminal. That's by definition. So there's kind of a link between the concept of an NPDA's start state and a grammar's start non-terminal. As we notice that, we're going to find that the transitions naturally happen within the grammar. So the terminal in a right-hand side is going to tell us the character that we read from the input string. The remaining non-terminals are going to tell us what do we push onto the stack. What do we pop off the stack? And then the character on the left tells us what do we push onto the stack. So we have the character that we read in the input, what we pop off the stack, what we push on the stack. The other way around. It's totally the other way around. Because we start with this S, we need to replace that S with a SA. So this is what gets popped, this is what gets pushed. Sorry. So we can start by defining a transition that just adds the start non-terminal. So we can transition from an initial state to another state, pushing an S onto the stack, because we know that that S must be what resolves and turns into the entirety of the string. Then we just make the associated rules. So this is what I just mentioned. The S arrow ASA says read an A from the input, pop the left-hand side from the stack, and push the non-terminals from the right-hand side onto the stack in the order that they appear. So we combine all of that idea into a single rule. From that state Q1, which we are at when we read this S from this rule, so we know that we start in Q1, we can circle back to Q1, taking off an S and pushing on an SA, or taking off an S and pushing on nothing, since there are no non-terminals on the right-hand side of the other ORed production. Then you just continue making more rules for all of the associated possibilities. They're all going to happen in Q1. It just matters which symbol is on top of the stack, which is dictated by an S, an A, or a B. And these are all of the things that we can do in this grammar whenever an S, an A, or a B are on top of the stack. So we start to see how these stack symbols represent the non-terminals in a grammar, which is a really cool idea to link together, because I think they actually help you to understand each other. The fact that you can do this to a grammar and do the same thing to an NPDA starts to make you realize that these ideas aren't actually that separate. They represent the same idea. Just, it takes a particular form of that grammar. You have to manipulate it into a particular form, where it's in the form that's easily translatable to the ideas of an NPDA. So we make the rest of the transitions. And in general, you just continue the process for each production as you convert from a context-free grammar in Breitbach normal form into an NPDA. There's one last transition. Once we handle every production in the grammar, we need the transition, the stack is empty, transition into an accepting state, which allows us to say that once we're done, we've removed that S from the stack, because the very first thing we do is we push that S onto the stack. If we can get that S off of the stack somehow, then the characters that we've read past, if we're at the end of that sequence of characters, then we must be able to accept the string. The grammar must be able to recognize that because we got rid of that S. We turned that S somehow into the entirety of that string. It's the same way that if we said something like S arrow, it was what, A, B, arrow, and I forget what everything turned into. This was A, B, B, B. And then we just, I think that was adhering to the grammar in the last slide. But if we do that, then going through this exact same process that you would use to derive this string in this, using this logic, is exactly what you would use to say, we're gonna read past the A on the string. We're gonna pop the S off the stack, put an A and a B on, but you do it in reverse order. The B would be on the bottom, the A would be on the top. So when we evaluate the A, we read past the B as we did here, and then the stack would contain the BB. When we evaluate the B, that gets rid of this B and keeps a B on the stack. And then we evaluate this B, which moves past this, and you end up having moved past the string. The stack is empty, which is what allows you to transition to that accepting state. But it's the same equivalent of, we've seen and moved past these characters, we derived these characters with these rules. It's not actually anything different than how we have thought about producing strings from grammars before. It's now just in a state machine form. That's pretty cool. Any questions on that?
Here's number 4. Is that gonna, this step is gonna look like one arrow from each other state going to the final system?
It's just the one middle state that we've been working on. Every other transition has been out of Q1 and into Q1. So this just says there's a transition out of Q1 on that empty stack character, the bottom of stack character, that reads nothing because we're already past the end of the string. How are we doing this? Does that connection make sense? Do you feel like you know how to do that at this stage? Practice on homework, possibly. Yeah. So some notes, I try to bring them into things, into the discussions, but yes, everything happened, all of the logic happened in Q1. And because everything happened in Q1, all of the transitions that were associated, it becomes easier to think about them in terms of just starting to write out the transition rules rather than drawing the diagram, because it gets kind of messy. That said, for a lot of the toy examples, it still might make sense for you to draw out the diagram.
But will we always consider it to be Q1?
Usually, it depends on the associated logic. Like last time we had the example where Q1 was pushing characters onto the stack and Q2 was popping them off, where we had to guess the middle in between. So simple NPDAs have a single middle state, but sometimes if there is a non-deterministic guess, or if there is a reason why the state changes in the middle of that, then you do need to break them out into multiple states. So knowing when to do that is an important part of NPDA design. But a lot of the times it just happens all in one state where you are pushing to and popping from the stack all at once. Let's look at another example, and I'll give you a chance to practice. Here's a fun grammar. First question I'd have for you. Are we in GNF? Do we need any conversion in order to get this into GNF? We do not. This is already in GNF, so you're ready to just go. So go ahead and either draw or write out the rules for an NPDA that is going to accept it. Feel free to butt your heads together, solve this together, and we'll come together and solve it as a class in a few minutes. So you see another eighth character. That's this strength here. Make that so. So have to go to. Yeah, this would be.
Do you go back a slide? Completely forgot what these are.
This one or one more?
Thanks for that.
You can also draw it as the diagram. This one is not so crazy complicated that you would not be able to draw it as a diagram. Either way, whatever would be better practice for you. Stack. So it's the transition. This is the from state, the character that's red, the symbol that's popped, the incoming state of the edge, and what gets pushed. So how many states are in this? Just to make sure people are on the right foot. I saw one right answer flash to me, and that was it. Four. That's close. Close, good guess. Is there any non-determinism here? Are we moving from doing one thing to the stack to doing another thing to the stack? We aren't. So this can be represented in just 3 states. Moving from the first to the second on pushing the start non-terminal, do everything from the second state to the second state, and then a final accepting transition to an accepting third state. So that's all we should need. So. And I just said, oh, you can't, sure. But how are you getting over there?
Oh, for the networks? I started, I didn't, yeah, I just actually just started last night. Yeah, but
What is due?
Friday. Yeah, it's actually, it should be pretty easy because pretty much half the code is from last lab.
Yeah,
The
exactly, yeah.
APIs. And then, yeah,
That was the same thought process.
yeah, just install Flask and to go. Same.
Nice to keep my,
Yeah.
So here's the base idea of the 3 states, the transitions from the first to the second and the transition from the second to the third. The question is just, what are all of the transitions from the second to the second? And that's going to be what we need to parse every one of these productions for. So let's see, how do we want to create this list? We're going to read an A, pop an S, push an A. We're going to read an A, pop an A, push an A, B, C. Read an A. Let's read a B. Read a B, pop an A. Push a B. Read an A, pop an A, push nothing. Because I ran out of room and don't want to draw quite that high, I'll do the rest of them down here. Which is read a B, pop a B, push nothing. And read a C, pop a C, push nothing. So those are the remaining transitions.
So we were thinking that maybe the example from Q0, from the transition from Q0 to Q1 would be the A as a big A transition.
Oh, yeah, to do this in general.
Yeah.
yeah, to do the.
So you could, yeah, the issue with that is how are you getting the S on the stack in the first place? If you allow for something like a self edge on Q0, you could put an arbitrary number of S's on the stack, which you don't want to do. So as long as you have some way of still doing that, that's a good idea to try to reduce that even further, but I don't think there's a way to do that without adding a 4th state. But that is guaranteed to be the first transition from Q1 to Q1 that you have to do. Once you've done this, there's only one transition you can make with an S on the stack, and there's no other way to get an S back on the stack. So rather than allowing this at any point from Q1 to Q1, one might argue that it's simpler to make a four-state linear system going from Q1 to Q0 to Q1 to Q2, putting on the S and taking off the S and putting on the AA, because that has to happen for any string that's in the language. So there is something to be said there. Is it more efficient? Easier to read? I don't know, it's up to you to decide. But you could do that. How do we do with this? Is this what we got at the end? Some more or less, some non-answers.
Partially, I don't know about others, but I was thinking on the first transition Q0 to Q1 that it would have the A instead of one. And
Gotcha. Yeah, the reason we have to is we have to get this S on the stack somehow. To be able to read this A, we have to pop an S. So since we start with the empty stack with just the bottom of stack character on it, we need some way to be able to do this rule. So we can't quite read the A yet, especially as we're pushing the S, because we only read the A when we pop the S and push this A, which happens in that row. So that is a great point, yeah.
In previous examples, we've assumed that the start non-terminal is on there, sorry, the bottom of the stack non-terminal is on there. Going forward, can we also assume that the start non-terminal is on there?
Yes, depends. For something like this, I would say, no, we need to push the start non-terminal on in some capacity, but if you did that, that wouldn't be the end of the world. It's an easy assumption to see that you are making. Any questions on this? Any further way that I can explain any of these transitions, how we come up with this diagram? You can see how this is way less fun than DFAs and NFAs, just in terms of the sheer number of transitions that you have here. As this grammar gets bigger, it's a pretty toy grammar. There isn't very much happening in it. You can just see how this state would just explode in complexity. You have just the sheer number of transitions into that state. And that would not be easy to visualize for a grammar even slightly larger than this, yeah.
I mean, it's kind of a nice hack, and if you ever have a language that had all find that it makes it super easy, grab out normal form grammar, you're like, oh wow.
Yeah.
This question just asked me to take this language and get a DBA now.
Yeah, it's a very easy process. It's just harder to visualize once you're done with that. And what do I have here? I have kind of a gross mess, but it is nice to be able to convert to the other because the algorithm itself is actually quite simple. If I asked you to write this up, then this program is not too hard to create. Because the structure is embedded within the string itself. It's just a matter of how do you break it apart and what do you do to it. It's just a few lines. Anything else before it goes away? Right. I think I have listed some of the transitions as well. So here are the associated transition rules. And so if you decided to write them out rather than draw the diagram, this would be what you would expect. Let's go the other way. How do you take an NPDA and get a grammar out of it? So let's think about that. What the stack has on it, just like the idea that we just made, whatever the stack has is an unexpanded non-terminal. So we need some way of each different stack character representing some non-terminal in some capacity. Couple of assumptions. There is a single final state in the NPDA that can only be entered if the stack is empty. If you have an NPDA where this is not the case, you can convert it into one. And then we have to ensure that each move either increases or decreases the stack count by 1. So we can no longer push a bunch of symbols, even going the other way from a CFG to an NPDA. We found that we could do that. We could push a bunch of symbols at once, but you could turn that into a sequence of transitions as well that go to other states and then back to the original, with just separating that process into one symbol at a time. And that would allow you to do that. So if you have an example like we had before, where we had our state Q1 and there was a transition that, I don't know, it doesn't really matter what it reads, but it pops something and it pushed 3 things. This is the equivalent of having some state, similar state, and we just say now, we, on this edge, can A pop an S, push an A, and that gets you to this state, which doesn't read a character, doesn't pop anything, and pushes a B, and then comes back with doesn't read a character, doesn't pop anything, pushes a C. So we turned this one edge into 3 edges that do the equivalent, and now we don't have anything that increases or decreases the stack count by more than 1. So you can make an equivalent set of transitions out of this that work exactly the same. So we can always convert an associated NPDA with either of these assumptions into an equivalent one that adheres to them. I think that's an important thing to recognize whenever we make assumptions.
Is the form also going to be the grab up form when we're done?
Let's find out. It's a good question. Yeah, it's in the textbook. I actually don't know off the top of my head. It ends up being, if not, then it's very similar to it, but it actually might be. But yeah, oftentimes if it's a very similar process to something that we've already talked about and it does that, it's important to note that sometimes you need to make these kinds of assumptions and manipulate the form of the object that you're taking as input. So we've spent all of this time talking about NPDAs using non-determinism built into these automata to represent context-free languages, and we haven't talked about determinism at all. I hinted at this a couple of times, that deterministic pushdown automata are actually a separate class of languages from non-deterministic pushdown automata. They don't map to the same language that can be represented, or the language class that can be represented by context-free grammars. And that's weird. So first, think about what assumptions have we made with an NPDA, and what would we have to change in order to turn it into a deterministic state machine? What was the difference between an NFA and a DFA? What restrictions did we have to place on an NFA to turn it into a DFA? What are the similar ones here? Yeah.
We can have lambda transition.
Yeah, so we could have lambda transitions in an NFA, and we could definitely have lambda transitions here. What's interesting is deterministic PDAs also allow for certain kinds of lambda transitions. The issue is, what is the distinction? What kinds of lambda transitions are allowed and which ones are not? Any intuition on that question? Yeah.
There's gonna be lambda transitions that will hop and push something forward.
Interesting idea. It's kind of on the right track. Yeah.
That you can have a lambda transition where nothing is read, but you can't have something where nothing's put on the stack.
Yeah, so it turns out that we're going to start to distinguish between pairs of characters that are read and stack symbols that are done. And we cannot have 2 different transitions out of the same state that both read the same input character and have the same stack operation, which includes lambda. But we can have a no-op on the string and do something on the stack, as long as we don't have another no-op on the string. So we end up with a bit of a restriction on what we're allowed in that sense.
So each
each state needs the cross product of our terminals and non-terminals as
It-
transition.
It's the cross product of the symbol that's being read in the input and the stack symbol that's being operated on. Yeah, so we can only have one transition for that tuple, basically. Yeah, only one move can be made for a given input symbol and stack top. So when we read on a particular stack, we pop that symbol to read it. That tuple can only have one transition defined for it. That said, because now we have a stack going along with the input symbol, it is okay. It's a distinct transition if we read the same character but do something different to the stack based on what's on top of the stack, because that is a separate state. The state that we care about in an NPDA or a DPDA is now that tuple. So lambda transitions are possible for certain configurations, but you cannot have an additional lambda transition that consumes the same input character. So why do we still allow lambda transitions? Because we really are thinking of this just as a tuple, honestly. And that creates a distinction for the value of the tuple. It's almost worth thinking in a DPDA that a state is not just the vertex of the state graph. It's the combination of that vertex and what's in the outgoing edge. The tuple from the outgoing edge defines that transition. So one way that I like to think about determinism is just stating that at any point in time, at most one move is possible. You cannot have any ambiguity on which move to make. So if you're looking at what is the next input symbol, what is on top of the stack, you need a unique move for that combination. And it's funny to note that we could regularly and freely convert between DFAs and NFAs, but there are some languages that are context-free that do not have a DPDA. You can write a grammar, a context-free grammar, such that you cannot create a DPDA. You can create an NPDA, but no such DPDA exists. So only some NPDAs have an equivalent DPDA, which is interesting. With the last few minutes of class, let's try to give you an example. So two languages, L1 and L2. L1 is A to the n, B to the n, and L2 is A to the n, B to the 2n. So why is L1 context free? Yeah, we could make an NPDA for it in terms of a stack. You would just push on something for every A and then map all of the B's that come after it to something that you push onto the stack. What about the second language? Why is the second language context free?
Say it's also context free because you can just push two things from the stack instead of one.
Yeah, exactly. So if we're trying to map to A to the n, B to the 2n, every time we see an A, we push two things. Whenever we see a B, we pop one thing. And that makes sure that we put on the same number of symbols as we popped off. It's just that when we push two things when we saw a single symbol. And that tells us that we are mapping one A to two Bs. However, what happens when we take the union of these two languages?
We didn't find two transitions for when we see a B.
We see our first A. Do we push one thing on the stack or two things on the stack? There's no way for us to know. What's nice is in an NPDA, we can recognize that. In a context-free grammar, we can recognize that. But imagine trying to make a deterministic pushdown automata that represents this language. You have non-determinism. You need to have two separate processes, one adding one to the stack and one adding two to the stack, and check, does one of these threads eventually succeed? Determinism doesn't allow us to do that. We have to go check one and then the other. The issue is that we have to do that with a single pass through the string from left to right. So if we could pass through it twice, then we'd be able to do that. One pass through it is going to add one thing and check and see if that succeeds. And then a second pass through will add two every time we see an A, and then we pop one when we see a B and we see if that succeeds. But we don't allow for that. That becomes more of a deterministic type of search rather than being able to handle this in one pass. Yeah,
When people talk about two pass compilers or multiple pass compilers, is this what they're referring to?
not quite. It's more of a, that's mostly used when compilers are optimizing and trying to convert what is there into something that is in a lesser form, and then so it's trying to make the program more efficient
Gotcha.
underneath the hood. But that's a good connection to be making for
That's
sure.
more like finding out if DFA is minimal, you do passes because it changes.
Mhm. Yeah. The new structure might have some additional opportunities for time saving based on that new structure. So do people see why this non-determinism can't be handled by determinism, and why you could construct something like a context-free grammar for this? You would just like we did before with a union, you would say S arrow S1 or S2, where S1 is the start non-terminal for the first half, S2 is the start non-terminal for the second half, and we could construct that grammar. And we now say, all right, at the start, we choose one or the other. And that grammar represents that, and you could draw the same thing as an NPDA. But I will argue that no such DPDA exists for this language. So language is context-free, you generate grammars for both halves, and then modify the start symbol to lead to either. So you just do something like this, and you have a complete grammar, context-free grammar for the union of these two languages.
Well, for this example, wouldn't you just be able to simplify the union of the two into just L1?
Simplify it to L1, what do you mean?
Because for L2, you can have like any number of, is that any number of even B's?
Yeah, we need to, however many A's there were twice as many of those B's. So
Oh,
in the language, there's 10 A's, 20 B's, or 6 A's, 12 B's. And the first half, you have the same number. So 6 and 6, 12 and 12, 20 and 20. Yeah, it's tough to know because you have to make a decision immediately and make the correct choice deterministically. Are we going down the path of S1 or the path of S2? And there's no way to know that as you look at the first A. There's just no way to know. Let's just, yeah, we'll come back to this tomorrow. But this is kind of the end of this idea, at least for now, as to why NPDAs and DPDAs are separate languages. And yeah, we'll come back to this tomorrow and continue from here. We are almost done talking about context-free languages. This would be exciting if what came next wasn't another pumping loan.
Yes,